Good evening and welcome. Beginning now, the international talk of the week, autonomous robots from design to navigation and interaction. Delivered by Professor Roland Siegwart, PhD, Director of the Autonomous System Lab of the Institute of Robotics and Intelligent Systems at ETH Zurich in Switzerland. The talk will last for 1 hour. After that, there will be 15 minutes for the public, should they have any questions. Without further ado, please welcome Professor Roland Siegwart.
Thanks very much for this nice introduction. It's really a great pleasure to be here and a great honor to be in front of so many young people which are excited about technology and engineering. So I will try to report a little bit what we are doing at our lab in Zurich on the design and navigation and more and more also interaction with mobile platforms. So let me first start with somewhat a little bit of historical view. Robots are around since quite a while. You probably all know the robots which are producing our cars. It's about 400,000 every year which are installed in factories, a lot in car factory, but all other factories. Meanwhile, actually, it's about 30% of these robots are installed in China. And they're not installed in China because labor is extremely expensive in China, but because they are much more reliable, much more precise for these type of tasks. Now, you might then ask questions, why do we not have robots around us? Because there is also some tasks which are not fun to do. But if you look here, these robots are in an environment which is very structured, very precise. It has no humans around, and for this type of task, robots are perfect. But the next type of robots, and this is actually the robots I will talk about, if the videos work, is this type of robots, which hopefully at one point probably clean up our kitchen. But I have to tell you that it's probably not tomorrow. It will take a while. Even if this video from Boston Dynamics, which was on YouTube, and probably a lot of you have seen this, looks like that, yes, we probably can soon buy this robot. But this robot was teleoperated. It was precisely pre-programmed. There is no way today that we have a robot which can really enter into a building and just you give him a task, clean up the kitchen, and he will load the kitchen. What these robots can do is, of course, today autonomously move around. They can actually go upstairs, they can get back on legs, but still they have a lot of limitations. Now why? Okay. Why is it so difficult? It looks like the tasks which are difficult for us, like for example, precisely soldering something or bringing something together in a car, is easy for robots. And the other side, jobs which are easy for us, is very difficult for robots. There's another example of a robot actually doing some work in a somewhat homemade environment. This robot is actually, the video is sped up 50 times. So even if it is 50 times faster, it doesn't look so fast. Why is it difficult? Our daily environment is very complex, very diverse, and a lot of surprises. And robots today cannot really deal with surprises. So these robots have to deal with uncertainties in their perception. So they have a lot of errors, a lot of noise in the perception. They have to deal with partially available information, so that you see only a part of a body, for example, from a person. They have not only to understand and see the environment, they have also to be able to feel the environment. And this is probably the most lacking sensor. Today's robots have no tactile sensing. We can actually handle objects very easily because we have a very tactile hand. Robots cannot do this. And it's even if there has been a lot of research, the progress is very slow on this end. We have then also torque and force control robots which we need. In the industry, in the factory, they have to be very precise. So they are position controlled. And they're much more precise than we can be. They can go in sub-millimeter precision. But in our daily environment, you rather go and try to contact an object. You have to be safe, so if you're touching a human, you should feel it, so you need force control. And this is much more difficult than but we'll come back on some elements of the force control. Then they have to be easy to program. Today's robots, they need specialists to program them. Typically, if you give a task to a friend of you or a colleague of you, it's only a couple of words. Please clean up the kitchen, and then you know what to do. We are far from being there. And of course, these robots has also to learn and adapt every day by interacting. So to make the whole thing forward, or bring the whole thing forward, you need robots which on one side have some intelligence. So we need tools from artificial intelligence, machine learning. But we need also, and probably even more, new elements like sensors, actuators, and the robot design. So a robot is not only intelligent, it's really an entire system with all the elements which have to come together. So I would like to go through more or less two elements. First, I will speak about designing robots with different examples from our lab. And then I will go over to navigation, how we can actually have robots know where they are so that they can move around in their environment. So let me first start with some example of designing robots. And I would like to start with student projects. I'm really extremely excited to see so many young people which are really excited about robotics. And we have also a lot of students which are designing robots. And these are two examples. We have much more wonderful examples of students which did in the last year of the bachelor project, studies, a project in a team, typically about 8 to 10 students. And in this team, they pose a vision themselves. Sometimes we propose something, and then they develop the whole system from scratch up to a functional prototype within 1 year. This is a choice the students can take. They can have a little bit less lectures, and they do more project-based learning. And we have a lot of very interesting collaborations. We have, for example, collaborations with Disney. Disney has a research center at the campus in Zurich. And so Disney has a lot of different places like the Disneyland, it has films and so on, but they have also resorts. They have hotels on the beach. And they came up with the idea, can we build a robot which can actually make drawings on the beach so that people are really excited about in the morning if they look towards the beach. And so the students, they've started to build a robot which can actually scratch into the sand. They had to build the entire system, and then they had to actually design the whole navigation, localization so that the robot knows where it is, then also the whole planning. And here, this localization is done by these pillars, which you can just put in as reflectors, which are seen by the laser which is on board the robot. And then the robot can take an image and then automatically calculates the best trajectory so it doesn't cross too much over its own drawing. And at the end, it can really draw elements which is actually something which is probably not extremely complex, but it's really not easy. I think the students learn a lot on one side, and the other side is something which is very difficult for humans because robots can move very precisely. Another task we gave the student is, today we can, with car-like robots with wheels, we can in principle only go on flat ground. If there is little steps, it's already difficult. If big steps, no way. Now the question was, can we actually build a wheeled system which can not only go on ground, but also on the walls and probably on the ceiling? So what the student built is this little robot, which is about probably 50 centimeters long, which you can see here, which is like a car, has 2 wheels in the back, fixed, and then 2 wheels steered in the front. But these wheels are not actuated, no motors on the wheels. But then they added somewhat the components from flying robots, so it's 2 propellers. You can see 1 and 2. And these propellers can be tilted in 2 directions. So with this, you can generate forces with the propellers. And you have to generate the force so that the robot is, for example, sticking to the wall. You have to generate the force so that the robot, the gravitation force is overcome. And then you have an additional small force to propel this forward. And you need a lot of control. You need a sensor. You need a sensor which measures the orientation of the whole system. And if you put this nicely together, what the student did, you end up with a robot which is on a flat ground. There's a wall coming. It just changes the propellers appropriately, and then it continues as it would be on the ground. Of course, here you cannot hear the sound. of course it's loud. It's like a helicopter. So it's a lot of noise, but it can easily go on walls. This is a student project which was not defined for a specific task. It's just to see, can we drive on walls? Which students showed that is possible, and very often then all of a sudden people came. The civil engineers came to us and said, can we have these robots? We want to do measurements on bridges. And we did some project in this direction, but later on, we will come back on this, we decided to go with flying robots without wheels towards bridges. Now, another field where, as an engineer, I think you have to be excited about walking and the mechanism how dogs or humans can walk. And walking, of course, is extremely agile. You can go upstairs, you can go in the mountains, you can go in a very rough terrain. And if you see in the nature as humans, but also as a dog, and this is a jumpy dog, where you can find YouTube videos of this jumpy dog, it's amazing how dynamic, how agile they can walk around and or make big jump. And so as engineers, we ask ourselves the questions in research, can we do something similar? And of course, the first thing then you have to try to understand, why is actually nature or humans and animals so good in jumping and so on? And there is one secret or one element behind is that we are elastic. So we have muscles and tendons, and the tendons are like springs. And this helps a lot, and this can also be done technically. So what the springs are doing in the human body, but we'll see also for the robot, is on one side you can store energy. So once you step down, if you're running, then the spring is actually compressed, and then you can release the energy. So you can recover about 70% of the energy, which you would otherwise lose if you don't have a spring connected with the actuator. The second thing, which is extremely important also, is that the spring actually damps or reduces the impact force. If you have no spring, with a contact on the ground, if it's rigid, nearly no compliance, then huge forces will go directly in your spine. And then you will be hurt. And the third thing is that the deformation of the spring, the movement, is directly a very precise measurement of the force, which is the interaction force. So in principle, you can do something similar with as the human body or the animal bodies, where you have a motor. In this case, it's a linear motor, and then you have a spring, only to visualize how this works. And then you can see each time you get to the ground, the spring is compressed, and then you release the energy, and you can do this also for the rotational element. Now, of course, this is only a model to give you an impression how this works, and then you can implement this on a real system. And what we did is actually implement this in a motor, which looks like a motor, but this is a motor which has first a motor, then we have an encoder, then we have a spring, it's a torsional spring in this case, then we have a second encoder, we have two encoders because then we can actually measure the deformation of the spring, and then we have the output. And of course there is a reduction gear. And in this motor we have a reduction of about 1 to 50. And this reduction means that in principle, if you would like to turn the motor back from the arm, it's really hard to turn it. But because we have a precise measurement and we have this compliance, we have actually a system which all of a sudden behaves nearly like a robot, a human arm. So first of all, you can see here, because we have a very precise force measurement, the behavior of the motor is like free pendulum, even if you have a very strong reduction gear, because you are measuring the force and you are actually controlling it to zero torque. Then the second thing is that, I have to start the video again. Oh, doesn't work. Sorry. So the second element you see, of course, because you have the spring, you can actually hammer on the element, and the gearbox is not destroyed, which would be destroyed if you have no spring in between. Then you can actually also have safe interaction. So if a human with your head are interacting with the robot, it will automatically stop. It has a very precise measurement. The spring is already damping or reducing the impact force, and so it's really a safe system. And you still can have a very precise position tracking. You can still go in very precise position. Now, these motors can be used for robot arms, or you can be used actually for the walking robots. And if you have, for example, here one leg of a walking robot, you can see again, this is motors with high reduction gear, but they behave like zero torque, because you can precisely control the torque. Now, if you then equip a robot, walking robot, this is a robot with four legs, and each leg has 3 motors of this type, so that you have enough degrees of freedom to move around. You can then very adaptively move around in the terrain, because the legs are compliant, so you adapt to the terrain. You can also go upstairs and always feel how you're interacting, and even do jumps. So this robot is not optimized for jumps. You probably have seen some of these similar robots from Boston Dynamics. You can, of course, optimize the spring so that you can do very high jumps. Here, this robot was optimized to really do inspection, for example, of environments. So you can see here an example where the robot is on an oil and gas platform out on the ocean. And the task of this robot is to go and do inspections with its onboard camera. And here, a wheeled robot will be limited because there are stairs and so on. And this robot can really move in all environment, can go on the situation, and can actually then do the inspection and do a 3D map of the environment, for example. So these type of robots have a new applications field, because they can really reach areas where you cannot reach them with regular wheeled robots or something similar. These robots can also fall down. We have seen this in the first video. And now the question is, can the robot learn to get off on the legs? Falling down can happen in all different situations. Sometimes you're on the back, sometimes you're on the side, and so on. And it's very difficult to actually control and model all the different situations and find always a good trajectory so that the robot can get off on the legs again. Here, for example, today, machine learning can do a good job. So if you have a good model of the robot, you can learn actually to get on the feet from all different kind of situations. And of course, you could do this by using a robot or 100 robots and put them in different situations, and then it learns. If it gets on foot, it's a positive reward, otherwise a negative reward. But you can imagine you will damage the robot and it will take forever. But if you have a good model, you do this actually in simulation. And in simulation, you can have 1,000 robots in parallel from random directions. And so this is what we did. We had robots. We learned to get on the feet again. So all the positive movement were positive reinforced, and the other one negative. And then we could directly use this controller on the real robot, and you can see the result is quite impressive. In very weird situation, the robot always gets very reliably back on his legs. So the robot learned actually to get this back, because this modeling, even if you can model very precisely the motion of the legs, but you cannot so easily model all the different situations the robot can be in this environment. So I will focus now on the next step on the design of flying systems. This is the biggest part we are working on since quite a while. We actually wanted first, about 20 years ago, always make smaller and smaller robots. And at one point we realized that the smaller you get, the more difficult it's getting around obstacles. If you're a little stone, it's a huge obstacle for a small robot. If you look in the nature, it's the same. The smaller animals get, the more likely they will fly, because they're always also limited. So, and we started then to think about how can we fly, and it happened to be a good moment. So these quadrators or multicopters, you probably all know, and some of you have one at home, made a big boost in the last probably 10 years. But it only appears about 15 years ago. So why was this all of a sudden possible? It was possible because on one side we have this little device, which is an IMU, which is an inertial measurement unit, which measures the rotational speed and the acceleration in all directions. And you need this to control a quadrator, otherwise it's highly unstable. And you need good motors, ideally brushless motors which can really go and control very fast. And we started actually with this about 2003, and in 2004 we were the first time able to really have one of these quadrotors stable in the air. The idea of this concept was around before. We just had the luck that we had the right sensors together, and later on we realized that I think it was the first quadrotor flying in the air, 2004, and today it's some of the gadgets you can buy for even starting with $15, $20. Quadrotors, or everything which is rotary wing, is somewhat limited in flight time because the efficiency of a helicopter is very low. It's probably about 10 times lower than fixed wing. And so we started to think about if you want to do other tasks than only probably hovering and taking a couple of pictures, we should probably have fixed wing. And then we came up with the idea, how long can we fly with fixed wing? Especially outside, you have sun. And so we realized that it's in principle feasible to fly continuously, multiple days, if you use the wings as solid power cells also, and then you store energy in the battery. And so in 2008, we were able to show the first time that we can fly more than 24 hours with an airplane which is only about 3 meters wingspan, 3 kilograms in weight, total weight, or even less, and half of it is batteries. And we were very excited, and so we moved on, and I will see then, show you a little bit more on details what the newer airplane was. Another way to fly much longer is that if you have an aerial vehicle which is lighter than air, which is a balloon. And of course the balloons are typically not so easy to control, so our students then developed a balloon which is a combination between a balloon and somewhat like a quadrotor. So they attached 4 propellers on all the sides here, and with these propellers they can really control them in all directions. The nice advantage of balloons is that you can actually fly over people without taking the risk that if something fails that it falls on the head of the people. And they actually started also with a student project, last year bachelor. They continued then during the master program, and then they started a company. And now they are offering this so more for events. You can also have some of these balloons which have projector inside, so you can project something and fly in the air. Another way to fly much longer and still have this nice ability that you can vertically take off like a helicopter, which is really a very nice feature, is to combine this. And this is called typically this vertical takeoff and landing system. This is also known since quite a while. You have probably seen some military planes were available. It was never really mass produced because it's still difficult. With small systems, it's still a bit different because the scaling is so that it's easier with smaller system. And again, students started in the bachelor think about they want to build a robot. Actually, the first vision was that they can distribute parcels. They do delivery with flying systems. And they said we need to fly far, so we need a fixed wing, but we need to get off the ground vertically. And so they built a system which is today now sold by their company, Wingtra, which has 2 propellers in the front and has 2 flaps in the back. This is the minimal number of actuators to even fly vertically off the ground. Once you're off the ground, then it starts to fly like a fixed wing system. And with this, about the same size of system, with about the same payload, compared with a rotary wing, you can fly about 1 hour, even more. And with a rotary wing, with a helicopter, you can fly typically about 10, 15 minutes. This makes this system very special, and this is the opportunity now that they started to sell them. They sold only a couple hundred of these systems, and they're present in all over the world for mapping from the air and also for agriculture, not yet for delivery. And this will be probably another next task, and then the whole system has to be a little bit bigger. I already mentioned that we have these solar airplanes. We actually pushed this forward in 2015. We flew not only 24 hours, but then more than 3 days. So that because this system has even more power, it was optimized to its weight, and this is a little bit bigger. You will see some details of this. And then the last thing we developed very recently, started also with students, from the bachelor and then continue with master and now PhD also, is this omnidirectional helicopter, which I will also go in more details. So first is long endurance solar airplanes. What we first have to understand is that the scaling of airplanes has some very special effects. If you build a big airplane, you have to be concerned about the structural mechanics, because your loading of the wings is the limiting factor in principle. For small flying system, the structural loading is not a big issue, but the aerodynamics is getting difficult, because the smaller you scale, typically aerodynamics gets worse. And this is actually the same in nature. And this is a graph. You can see there is man-made systems like airplanes or birds on it. And you can show that there is a line which is actually the wing load and the weight. How the wing load changes with the weight. You can then have linearization, and this is actually the equation, and which says that the wing load really gets worse and worse the higher you get. So if you want to build big airplanes, you have to worry about the big wing load. And of course, for the smaller airplanes, you have to worry about the aerodynamics. And if you want to now build an airplane which can fly forever, you have on one side the whole total mass, which is composed of the structure, which you can influence. If you build it as light as possible, you are lower. Then you have the battery and also the solar cells. And on the other side, you have the aerodynamics, which defines you more or less the force you can generate to lift this mass. And you have to optimize. And then you have all the different scaling laws. And what we looked at is what really happens if you get smaller, because we wanted to have a very small solar airplane. And of course, with this, all this equation, you can then have the scaling law for different elements. With batteries, it's easy. It's linear with the size of the battery or the weight of the battery. It changes. For the structural loading, it's a little bit different. So it's not linear in total. And if you plug in now these equations, you come up with a drawing which can, for example, be represented like this. On one side, you have the battery mass. On the other side, the wingspan. And here you have the access time, which is the time which you can fly more than 24 hours in principle. This means with a sunny day in the summer in Switzerland, it will be in the winter from here, in the best sunny condition, you can have here, for example, an access time for 15 hours. This would mean, in principle, you can fly a whole day without any sun, and you can still continue over the night. And you can see then here, if you have a bigger wingspan, you're getting always a little bit to more access time. And if you have more battery, you get more access time. But if we have even more battery, all of a sudden the battery is an extra load, and then it reduces again. So you have somewhat a very flat optimum here, which is at higher size. But we wanted to have something small, so we selected to go something we like 6 km. The selection is actually based on the idea that we want to have a hand lounge, so that somebody can really lounge it. And so at the end, we had a system which was designed and optimized, which is about 6.5 or 7 kilogram weight. It has 6 meters wingspan nearly, and half of the weight is actually batteries. It's mainly batteries and then the structure. And we did this test in 2015. So here you can see how we can launch this by hand. This is one of the main PhD students designing. Oh, who was designing this? Again, oops. Then, of course, you have then also overnight. During the night, we had lights on so that people could see it. This flight was, on principle, fully autonomous, but we had always backup people. Then we had the idea to fly at least about 3 days. We could have continued, but it's tiring for the people watching always the airplane. And so after the 3rd day, all of a sudden we had a storm coming up. And you can see even the computers were blown away. And this was a critical element. These are very fragile airplanes. And so we had this backup pilot, which was intended to land with the airplane. But he realized that he cannot land it because they are very lightweight, have big wings, and so they are like a paper in the air. And so we decided actually to use the automatic landing, which was not extremely tested up to now. And you can see that the system was doing a very nice landing. So in some sense, of course, computers can do a lot better job to very precisely operate the system. On the other side, to take high-level decisions, humans are still better. So in the second part, I would like to focus on the agility of flying robots. And this is, of course, not with fixed wing. This is more with rotary wing. And with this quadrotor compared with the standard type of helicopter with one main rotor and a tail rotor, you have much more agility. But it's much more unstable. You have to control it always, but you can fly very dynamic. And of course, once you have dynamics, you could, the next step would be, can we actually even interact with the environment? Can we have a robot arm there and touch something? So we did some work to add first just a simple robot arm with 2 degrees of freedom, which is actually also a compliant arm, which has an elastic element in. And then you can see the PhD students who developed this Mina can really touch a flying robot, and it feels that you are in contact with it, and it will go back. And so in the other way around, you can actually go to a wall or go and grab something and really feel what's going on. But you can still see if you're touching, in order for the helicopter to come back, it has to tilt. So it's somewhat not ideal, because today's quadrotors or multicopters are typically having all the propellers in the plane. A second element of this flying vehicle is that you are limited with the payload, and it's very difficult to make much about it. But what you can do is actually to have multiple of these helicopters together. It's the same what we do as humans. If you go and want to carry a table around, you typically ask your friend, somebody's guiding, so you're walking, and the other one just follows. And this you can actually do also with helicopters, where we have here a concept that one is the guide robot, which has fully autonomous flight capability, knows where it is, and the other one is just carried behind. The other one has only to know at which height it has to fly, and all the rest is actually done by the force from the first robot. So flying platforms have some nice features, which is not the same for wheeled robots on the ground, because you have resistance on the ground, but in flying in the plane, in principle, you have no resistance. Now, but still, if you want to move forward, you have to tilt the system, then you have some problems probably with the connectors. So this was not enough, and we went on and thought about, can we actually have flying platforms which really can fly in all directions? These multicopters, and they typically have only 4 degrees of freedom you can freely choose. So it's X, Y, Z, and then the rotation around the central axis. But in order to move forward, they have to tilt. They cannot move forward without tilting. And so they can also not so easily control and generate forces in all directions. So then students sat together and said, what can we do about this? And actually the solution is pretty simple. So you have this, in this case now 6 propellers. They connected it to a bar here, which you can turn. So you can turn the propeller. And so you have, all of a sudden you have, in this case, 6 propellers, and you have 6 rotation, you have 12 actuation degrees of freedom, and in space you have 6 degrees of freedom. So you have a highly overactuated system. So you're really doing the opposite, so all of a sudden you have not an underactuated system, and you have a lot of potential. Then you have more a problem that you have to find a mapping from your force, required force and torque. So typically you calculate, depend on the motion you would generate, or the speed you would generate, a torque and a rotation, a thrust force and a rotational force. And now you have to map this to the forces and the orientation of the arms. And this is then not so easy, because you're overactuated. There's multiple solutions, there infinite solution. But the students found a way to make a mapping which seems to work pretty easy. And once you apply this, then you all of a sudden have a system which can not only fly in a plane and actually tilt in when it moves forward, but it can fly in all directions. Which means also that you can generate forces in all directions. So you can have, in principle, be like this and then generate a force against the wall, or be like this and generate the force against the wall. Now, of course, the first thing is, it's probably academically nice, but what can you do with this? But of course, once you want to fly not only in the free space, but also in interaction, for example, doing something on a wall, then this is extremely helpful, because with other robots you cannot do this. And here you can see an example what you can do with such a system. This is not a system which is symmetric as we have seen before, but it had also two propellers in the front, which you can see here and here, which can be rotated in both directions. And there is a smaller tail propeller. And with this system, you can also fly in somewhat all directions, and then you can go in contact. And we have already now some very interested people, people which are interested to do measurements on their infrastructure, to go and connect. For example, for wind turbine, they want to measure the propellers so that they're still safe. And so you can go and get in touch. You can go straight, and this you can more or less also do with a standard helicopter. But now at one point you want probably measure also against the ceiling, and you can see you can just rotate and then you measure against the ceiling. And something what we did more recently is actually we just put a drill on 3D dense reconstruction, because you have to do collision avoidance. So you need not only points where you can localize to, but you need to know that there is a wall, and then you need a planning. And all these tasks are pretty calculation intense. For flying robots, you have to do this in a way that you can do this on board in real time, which is not so easy. And you can see here what we typical system in our lab now has together today. You have the first sensor unit with an IMU, which is mainly for the control of the attitude of the system. This is more or less the lowest level. We have then a visual inertial sensor, which is a camera and an IMU, inertial measurement units together. Then we have sometimes also depth cameras or thermal cameras. And with these cameras, you can build depth maps, dense maps. You can also use some of this information only for localization. And of course, you need then also local and global planning. And I would like to go in some depths in some of these elements. Let me first start with localization. So localization you can do by actually trying to find points in an image and track the points. So imagine you have this image. This is the main building of ETH Zurich. You try to find in the image you lose the depth. You can recalculate the depths. And this is intuitively very easy to understand. It's somewhat triangulation. So you have two images and you do this triangulation. And then you actually know where the robot is or the camera is. But you also know all of a sudden back where the depth point is. And if you do this nicely, and this we did a lot of collaboration with Google. We implemented this first also on Google Tango device, which is actually a smartphone. And today, it's in the newest smartphone, it's integrated this stuff. You can actually, in smartphones, you have cameras. So you have exactly this. And you need a second element, which is the IMU. And you need this because otherwise you don't have the scale. So the scale information is missing, so you have one parameter missing. But with the IMU, you can actually also estimate the scale. And then you can actually, on board a system, track these points. You can see the color points are the tracked point in the image. This is the measurement of the signal of the IMU. Now this is on a roller coaster, where my PhD student went on a roller coaster with the smartphone. And then you can see as soon as you move really around, the accelerations are big, rotational speed also. And what is interesting here, this is the smartphone actually doing a motion estimation in real time on board. So it knows exactly how it's moving in 3D space on this roller coaster. And this is exactly also what we need for flying robots. They have to know where they are and how they move around. So the tracking is first a motion estimation. Now once you put these points in a map, then you can build up a map, and then you have a localization. And then if you drift a little bit away, but once at the end you are coming back to the same place, you can correct this. And then you have a somewhat consistent 3D localization. For doing this, you need, of course, the appropriate hardware. Although I mentioned, on one side you need a camera, on the other side you need the IMU, and you have to integrate them. And you have to integrate them considering all the uncertainties. And typically it's either a Kalman filter or a filter or an optimization problem you are solving. So where you're plugging in actually the landmarks and the measurements for the landmark and the tracking, and on the other side also the IMU. IMU is faster, so you can actually have more entry. But if you want to bring this together and then solving this optimization problem, you have to have a very precise time stamping. So you have to know exactly when it was taken, because you are in movement. If you don't know exactly when the image was taken, you introduce errors. So this was not so easy to find it on the market, so we had to develop our own camera. Today there is some systems which have this integrated, where we have a very precise time stamping. So we know exactly when the images and the IMU measurements are taken, and thanks of this you can be extremely precise. Now, why is this interesting on smartphones? This is because of virtual and augmented reality. If you have virtual reality with the goggles, but more and more you have this also on the smartphone, you can look to your smartphone. You need a very precise motion estimation of the device. Otherwise you get seasick, because you are overlaying more or less a virtual image which is related to your motion. So if you're turning the head, it should really be real. And this you can today now do on smartphones. And if you see this, what happens, this is a view through the smartphone where we have a virtual castle projected in a real environment. This is work which is done from some of my students, which now start in a company. And this is based on the newest elements which we have on the smartphones. It's in the iPhone and also the Android phones, which are now available. And of course, this will get more and more funny and very nice applications. Probably some of more towards games, and some, for example, really to do measurements in the environment, so that you can really easily measure a building. What you can probably do a little bit more realistically is this. You go with a tablet and you have an inspection task. You have to go to an environment like a building where you have to take measurements in an industrial setting. So the person, here is my PhD students, which is demonstrating this, goes from one station to the next. This is a tablet, and the tablet is building up a map, and is then precisely estimating the motion. So the blue points are the points where measurements are taken. The red line is the motion. And in parallel, it's actually collecting these features, which we have seen before, which are sticking out, which allows them to make a map. So this is then the map. Green line is the trajectory of the motion. The yellow points are the features, which is the map for the robot. It's more difficult for us to read it, but for a robot, this is the easy way to do. And then we give the same map to a helicopter. The helicopter has also a camera and also an IMU, more or less the same sensors. And you can directly use the same map for doing exactly the same job the day after. And where you don't have to really do something to control, so it's just doing exactly the same thing based on the same localization. Now, localization is not enough. As I mentioned, you have to also build up then a map and bring multiple maps together. And we have here a pipeline which is actually even available open source, where we have first local map creation, and then we can even fuse multiple maps. Local map creation, first of all, you need a motion estimation, which is here done a little bit differently. We have used only simple patches, and these patches allow us to track them from one image to the other. Tracking of patches is very fast and very reliable, and you can go very fast with this system. Then, in parallel, you are actually collecting, again, these features, which allows you to build up a map. And then you have, for example, multiple robots, or multiple humans, which are moving around. They're building maps from different corridors, or for different levels. And then you have to bring these maps together. And so you have then different submaps, and at one point you have to fuse this map, and so that you can build a consistent map. All these maps will drift a little bit away, but here you first close the loops, and then you jointly optimize all the maps together. So you find the features which are overlapping from one map to the other, and then you align them, And at the end, you have a map which is typically in the order of magnitude of 1-2 centimeters precision. You can even push it further, which allows then for all the other systems to localize in this map. Now, the next step is actually to do this 3D dense reconstruction, which is not so easy with cameras on. If you have a laser sensor, you have directly depth information. With the camera, sometimes you're missing some information. It's not so easy to get this information. But if you have multiple images, you can actually build up a map. So you actually have a camera, and then you're always trying to find a point, which is the point which is the closest object you see in the camera. And then you bring this together, and if you have multiple of these images, you can actually verify this point and have it from different point of views. Then we are putting these points in a voxel, a grid, actually in 3-dimensional grid. And for each grid cell, you can actually calculate, how often has this been seen? How certain are you that there is a point there? And then with this, you build a 3D map of the environment. And you can see here how this works, and this again is online in real time on the helicopter. So the helicopter starts here, no view, then it sees more and more, and then it builds a 3D map of the environment around, together. And this is a voxel grid, so it's a resolution of typically about 5 to 10 centimeters, because otherwise you have too much calculation power needed on the helicopter. And you can see here it's the real image, and here's the map of this environment. And you can easily imagine that this map is actually good enough, so then that the helicopter can fly by itself, can see walls, can see where there is opening, and where it can fly in and do its inspection task, for example. The last thing you have to do is actually to find a trajectory in this environment, which is also not so easy. And typically there we have 2 levels. One is the global. So if you have a map of the environment, you can actually optimize and find the shortest path or the best path. But very often you don't have a map beforehand. So you have to have different levels. So typically for the global planning, you have one approach is this rapidly exploring random trees, where you try randomly, more or less, different connections, and then you try to get better and better. So you just try. And this allows you to have at least very fast a solution, but you never know exactly if you have the best part until the end, if you have found all. But on the other side, this is typically a graph which has not a smooth trajectory, so you are then smoothing the whole trajectory. But once you are smoothing, there is a risk that you're colliding with the environment again, because all of a sudden you're cutting around the corner, and then you have to optimize locally. And this is actually how this looks like. Imagine that with this RRT star, you find eventually this as the shortest path. You have a lot of other solutions, but this is then the best solution currently. And then, but it has a lot of corners, and you don't want to fly like this. So you are smoothing it out. But if you are smoothing, sometimes you have overshoot, and all of a sudden there is a risk that you're colliding with the environment. So as a next step, you actually have to locally optimize this system. And eventually, if you do this, you have then an ideal and very fast movement in this environment. And so this allows you then to have a flying platform which is able to localize, to build its own map, to build a dense map, and then in this dense map actually build also a 3D the trajectory and find the best paths in the environment. For example, you can then also color it and say which is the best, the less risky environment, and where you can actually go faster, for example, because you have enough space available from the distance to the environment. So with this, I'm smoothly coming already to the end. So I tried once to think about how can we define the complexity of robots. And in principle, there is probably 2 elements. I tried to put this in one graph and then put also the type of robots in this environment. On one side, you have the complexity of the environment. If you have a very structured environment, might be, for example, for a car, a freeway is a very structured environment. It's a simple environment compared with a city where there's a lot of dynamics. Or for in industry, typically you have a very structured environment. So this is this axis. And the other axis is the type of interaction the robot should do. Robots which are only moving around, it's very simple. because they don't have to interact, they don't have to have tactile sensors. This is a simple slide. This is in this direction. And the most complex is if you have tactile interaction. One example for a tactile interaction, imagine that you want to open a knot here with one hand. There is no way that, I'm pretty sure that in the next 20 years we will have a robot which can do this. You can imagine to build a special machine which does it once, but if you have different type of clothes, there is no way. And this we can do because we have such a tactile and then good hand, and we have today robots which have very limited hands. So in a way it's actually interesting. Helping in the household is something we can consider that kids can do this once they probably are 6, 7 years old. So it's not so complex. Driving a car on a freeway, we would not put a kid into a car. With robots, it's the opposite. Driving a car, so we are more or less there on the freeway. It's a structured environment. Cleaning up the dish at home, we are extremely far. This actually shows that there is really a different world. Robots can do stuff better than we can do in some situations, and we can do stuff which robots cannot do. And in a way, we can say it's probably also a positive sign. We can use robots in environments where we don't want to work, in environments which is dangerous, and we will have probably a lot of more funny and interesting jobs in the future, and the robots do the very bad jobs. Imagine that you would have to spray the cars which are built every day by hand. This is not possible in principle, and I think you cannot expose people to spray the whole day cars. Robots can do this. But on the other side, we have elements where the human, for example, in caring about kids or also helping in hospitals, I think there we need people which have all this quality that we can manipulate objects, we can have tactile interaction. And so you can see here household, I still have had the courage to put some timeline in. Here is 2010, so autonomous cars is in principle solved today, I think, on freeways. I think it's not solved in the city. In the city, this is autonomous car in urban environment. This is not exactly the green line, because then you have some sort of interaction. You have signs, you have a person probably showing, oh, go or go not. You can have to watch other people. This is very important. It's not important on the freeway, but it's important in a very dense city environment. So there is still a lot to do. I think one big element is that we have to have robots which understand the environment. And understanding is not so simple. There is a lot of people which think that now with deep learning we will understand everything. I have a lot of doubts, because we have already seen today deep learning needs a lot of data. It's very difficult to generalize, and it sometimes ends up with solutions which are optimized for something, and there is a little bit in other situation, it will totally fail. There are systems which learn, for example, to analyze the street environment with trees, humans, streets, houses, and so on. They are trained in San Francisco. And then you use the same thing in a city which is somewhat different in Japan. All of a sudden it totally fails. For humans it's no problem. If you drive in San Francisco, you can also then drive in Japan. So I think there's still a lot to do in understanding. Learning and adapting or learning algorithms will help us more and more, but it will not exponentially change the situation. I always claim that what Elon Musk hopes that tomorrow we'll have fully autonomous cars which really can go from A to B in all situations without a driver even inside. I have some doubts. This will take quite some time. But of course, if you want to have it today on the freeway, this is some cars are really pretty autonomous already on freeway because it is simple. This is on the lower end. So quickly coming back to where I'm coming from. So at ETH we have meanwhile a really nice group of people contributing or doing core research in robotics. So we have so more or less in the center the people which are considered robotics professors like Marco Hutter, Margarita Klee, Brett Nelson doing micro robotics. But then we have a lot of other people which are more in related stuff which are more and more applying their findings in robotics. For example, computer vision, we are pretty strong with people in this field, artificial intelligence. Then we have another group which is mainly in medical robotics, going down to very small robots or biological robots. And then, of course, also a strong control group, which a lot of these control people are mainly now focusing on control for robotics or and using their knowledge in this field. This actually allowed us to build up a really nice and strong ecosystem in Switzerland in robotics. So we have the two main universities, which is ETH Zurich, where I'm currently, and EPFL, which I was also 10 years there. So these are the two governmental supported, directly supported technical universities in Switzerland. Then we have a couple of more local, which in Brazil it would be the state universities. In Basel, they're doing a little bit of robotics, but they don't have really engineering schools. So they're doing, for example, medical robotics here in Basel and Bern, because we at ETH, we don't have medical school. Then we have also very nice joint projects, for example, the National Center of Competence in Robotics, where we collaborate with different universities, or probably which I even think is more exciting, is with the national competence in digital fabrication. This is a project which was initiated by the architects from ETH Zurich. And architects, our architects at least, I think they are artists. And so they're not engineers or not civil engineers, they're artists. So they want to build building for whatever shape. So they are hired to have always flat walls. Now, if you want to have curved walls or curved ceilings, you need robots, because humans cannot so easily do this. So we have a lot of very interesting projects in this context, and for us as roboticists, it's actually inspiring, because they are really bringing totally new questions in, where we can then get inspiration to build new type of robots. For example, for the flying robots, we are really trying to think now, can we do the flying robots to do really build entire walls with flying platforms? This research actually generated also a very nice landscape of startup companies. There is a lot in flying robots, but there is also some in medical robotics, and you can see here, this is more or less all the startup companies in robotics which came out of the ETH and EPFL in the last about 10 years. And I would guess that we have probably the highest density of really successful startup companies in the world, if you look at the size of Switzerland. And interestingly, there is also some side effect, and especially about this visual navigation, where ETH is very strong, so it's two other research labs are doing a lot of in visual navigation. These attracted actually all the big IT companies to Zurich. And this is not robotics in most cases, but it's about virtual reality and augmented reality, because a lot of these technologies are exactly the same, because you need this motion estimation, you need sometimes 3D reconstruction. And so we have now Google since quite a while in Zurich with a couple thousand people, but we have recently also Facebook, which came to Zurich. First they started to hire about 8 people from my lab in one block, and then with this they started a lab there. Apple has a lab in Zurich, but this is hidden because they're extremely secretive about what they're doing. Now, more recently, Microsoft started also be much stronger in Zurich in research, and Disney, as mentioned, has a joint lab, and so we have this ecosystem which is actually very helpful, because in a way, of course, they are looking for the same people as the startups, but on the other side, they can also help the startups locally. And I think if all this together allows us really to move a little bit faster forward, we have a lot of this technology which is needed for robotics. And so in conclusion, robotics is on one side booming. There's a lot of hype about robotics, but it's still extremely difficult. Robots are very complex machines. And this nice YouTube video sometimes really are extremely exciting. Boston Dynamics is extremely good in this. Up to now, they never sold a robot for a real task. So they still have to bring all this together, so it's not so easy. You can easily do a nice video, but you cannot easily do a reliable system. Robotics is, I think if you want to move forward, you need really top research combined with all the talents which can then bring this forward. You need a combination of precision mechanics, actuation, sensing, and artificial intelligence. So you have all these elements together. You need, of course, this entrepreneurial spirit to bring this forward. And in general, I think robotics is a wonderful field because you're touching a lot of different fields. You're touching all the engineering fields, but you're touching also psychology and sociology because these robots at one point interact. So as a last element here, I posted a couple of elements which show this booming and also risk with robotics. So there was, probably you heard about this, there was a hotel in Japan which was only robots there. So when you went to the registration desk, there was robots behind. And then you had, you can speak with robots. Then bringing your luggage into your room, robots. They closed it now. They, on one side, seen that people were not happy because at the registration desk, if you have a special questions, the robot didn't understand because it's very limited still. Then it was more expensive. They had to maintain these robots, which is much more expensive. And so people were really not happy and they have to close it. We have on the other side here an example. This is a startup company which came out of MIT and is actually the startup company of a professor which is now at ETH, Emilio Frazzoli, a control person. They built up a startup company called Newtonomy for autonomous cars. Small company still, probably about 70, 80 people. Some first results. They were bought for 450 millions by a big supplier company for a car industry. All of a sudden, they are extremely valuable. On the other side, there is another company, Rethink Robotics. They wanted to build the first new type of robots, somewhat the next generation of industrial robots, which are easy to teach and easy to interact and which are safe. They did, in principle, an okay job, but it's extremely difficult. And so they had 150 million invested and they had to close the doors about a year ago, or a little bit less than a year ago. So there's a lot of activity, a lot of changes and dynamics in it, but it's also fascinating. And I think if worth to go, don't go shoot for the stars, shoot for something realistic. I think there is potential today to do something with robotics. And with this, I would like to close, and I'm happy to answer questions or discuss with you. Thanks very much.
We, from the SEMATRON group, would like to thank Professor Siegwart for his talk. We have now 15 minutes dedicated for questions from the audience. I would like to emphasize that the questions should be concise for a better utilization of our time. If you have any questions, please raise your hand and one of our organizers will provide you with a microphone.
Thanks. My question is about how much of processing power from the embedded systems are needed to do for like a dog walk or like a drone, you go to the wall and stay in contact with stability.
Of course, it's extremely dependent on, for example, the resolution of the 3D map and so on. But probably I would start at another end. There was the first autonomous cars DARPA challenge about 14 years ago. The first cars there, they had the trunk, big cars, SUVs, full of computers. Today, you do the same thing on a really good laptop. So what we have on the walking robot, this is typically the power of a laptop, a good laptop. On the flying platform, we are a little bit lower because we don't have the power and we don't have the weight, but it's not too far. So it's somewhat probably the power you had with a laptop about 4 or 5 years ago. But with flying robots, it's really a challenge. So this is one of our main goal, really to try to do this real-time onboard. And you have to do this, otherwise you cannot have a safe system. So you have to be able to see the environment in real time and avoid collisions. And you cannot go through a wireless communication, which sometimes fails. So you have to have everything on board. Just shout loud.
You showed us fully automated plane landing at scale. How close do you think we are from a fully automated airplane to
On one side, I could say we have it already since quite a while, because the big passenger plane can actually, in principle, fly from A to B without any intervention. They can land and get off the ground. So it comes back to the question if should they be able to decide in all crazy situations. The airfields are very structured environments, so it's not a very difficult task. But if in a case of urgency they have to do something else, then it's getting difficult. So in a way, I think we are technologically pretty close to having this, also for small drones which can then land in different spots. But it's still there is still a couple of open points, and if we would enter all these drones in our airspace, it's quite dangerous today, because they, for example, cannot reliably see other airplanes, and then you might have collisions. And the more drones you have in the air, the more likely you have collisions. So I think we are close. In the free air, it's easy. As soon as you are landing or getting to infrastructure, it's more difficult. You have to have onboard vision. Collision avoidance with others is still not solved. And the smaller you get, the more difficult it is to have appropriate sensors. Big airplanes have radars. We are working on small radars for the drones, but this is not so easy because you limited power, limited size of the antenna, which then doesn't allow you to do everything. So there is today I think about already 50 or 100, I think roughly 100 companies which are working on autonomous taxis, flying taxis. I personally would say it's too early to invest in something like this. To build a new airplane which is approved with a pilot in it, it typically takes about 10 years. If you have then to approve also autonomous flight, it takes probably another 10 years. So I think we are probably 10, 20 years down the road. But it's fascinating, of course, the idea to have somewhat a small flying vehicle in front of your door, and then you sit in and then it brings you to whatever place you want. It's a funny idea. Once you start to think about, if you have hundreds of people doing this, helicopters are loud. All of a sudden you probably are not so amused anymore about this idea.
Hello. Well, I would like to know if it was more challenging when developing a visual-oriented flying robot to develop the program that processes the images, or building a hardware that's not only able to run these programs, but also light enough in order not to get the robot heavier than expected.
It's probably a difficult question, but there is probably one answer which is not a very clear answer. But on one side, really perceiving and analyzing situations, I think this is still an open challenge. Now for the calculation power, this is in a way easy because you just have to wait. Because calculation power is really developing very fast. For example, also sensors. We had the first prototype flying in the air. The sensor was $2,000 and it was big. So we could not fly on a small platform. Today, it's not $2,000, but less than $1, because you have all these sensors in your smartphone. And they're even better. So 10 years later, the problem is solved. But the problem of understanding, because today we have images which are much higher resolution, but this does not imply that the computer can better understand the situation. I think this element is moving much slower forward. Now we have some nice success with deep learning. The concepts are still not more or less the same as 20 years ago. But now we have the calculation power. But now we are again learning what are the limitations of these concepts, and so we have to develop the new concept, and this is slower than just calculation power.
Hello, Professor. Good evening. I have a question regarding the use of aquatic robots. I don't know if it's your line of study, but what can you say about this field? Is it worthy to be studied, as we don't know much about the ocean?
Yes, so we had 4 student projects where the students built different type, swimming robots, fish. We had a couple of projects, and I think it's worth to, because there could be a lot of useful tasks for robots swimming or diving or whatever, but there is also one extremely big challenge. There is no communication in water, nearly no communication. Electromagnetic waves don't work. So once you are diving down more than half a meter, your wireless will not work anymore. So you could imagine to have sound. Ultrasound could work, but this is the bandwidth is very limited. So you can probably get one byte every second. So if you're far away, because it takes time and it's slower. So this is a very limiting element. So you need systems which are much more fully autonomous, because you cannot interfere. So if it's diving down and doing a task there, you have no communication. Of course, there is a lot of solutions where you have a tether, you have a cable. But once you want to go far, you don't have a cable anymore. And we would probably do a little bit more, but we have no oceans. So in Switzerland, we have lakes, but it's not so fun in the lakes to do robots. But it's a very interesting field, and I think it's even also for measuring and cleaning the ocean, there might be more robots also. Can you repeat there? Yes, so we have actually agricultural robotic project. It's in principle the application which I think is most urgent and probably most useful for the world population. I am convinced that robots can really help us to be more sustainable in agriculture. But it's also a tough task. But for example, you can learn with robots. We had a European project where you can learn to find the plants, and then you can actually destroy the plants which should not be on the field. But it's still a complex environment, so it's step by step. I see that also here you make a lot of projects in this field, and it's difficult. Plants are actually also very dynamic. So for example, for localization, in man-made environment in the city, it's getting easy because a lot of the structure is static. It will not move. On the field, everything is moving. So you will not be able to localize on your images, because next day or day after the plants are different, they have grown. So already this is not so easy. So there is another challenge. But in a lot of fields, we're working now on some elements where we have a couple of specific markers. In general, in big fields, if there is flat, GPS is pretty okay. In Switzerland, we have mountains, and then we have rifts, and then all of a sudden you have reflections, then GPS is not okay anymore. But I hope, and I'm happy to, I will see, I think, tomorrow and after tomorrow some of agriculture stuff, because Brazil is very strong in agriculture, and I think for you it's an opportunity to do better and combine this, actually your strength in agriculture with the strength in robotics. this is difficult to say. Of course, there is in the beginning it's revolutionary, and then it becomes standard. We learned actually only later, but the first control of the quadrature, which happened to be in our lab, because the technology was somewhat a little revolution, and now it's picked up. DJI is producing millions of these devices. At the moment, I'm extremely excited about this omnidirectional flying platform, because there we can really do all of a sudden something which is in principle not foreseen for flying robots. Also, airplanes are typically not there for pushing stuff around. It's only to move from A to B. Now with this new type of flying platforms, we really can push stuff around. So we will, hopefully in about 3 or 4 weeks, we will have a flying milling machine. For a simple test, but we will have one of these robots with a little mill, and then we'll try to sculpture something out of foam, which makes, because these systems have very easy access to all sides. You could do the same thing with a robot arm, but if you want to sculpture a cow, for example, in real size, you have to go around. Then a robot arm is not flexible enough. But if a flying platform, you can do something else in all directions. But in general, I think I'm most excited about all this crazy and wonderful projects students do. We had just actually, before I came, we had a final project demonstration of the student project again. So one student team developed a robot, which is a fixed wing flying platform, which can also dive. So they really fly into water, put the wings down, then they dive into the water, go underwater, and then they dive out again. We don't know what is useful, but I think it's still that during your studies you should do some challenging elements, and very often you learn something anyway, and very often you all of a sudden you see a use. Yeah, radical new ideas are typically not coming out only of the usefulness that you first say, I'm going to solve this, because very often you develop something which was never around before.
Hello, can you hear me?
Now it's try again.
Can you hear me?
Yes.
Yes. Thank you for the lecture, Professor. My question is about, as you said, the robotics industry is booming right now, but another field that is booming right now is space exploration. And my question for you is, what do you think is the short-term autonomous space exploration with robots? What do you think is, how do you think it's going to be?
Of course, I think this is somewhat much more in the future, because space exploration, at one point you need probably really totally new system which can do everything. Of course, there is some ideas to at one point go on Mars. If you want to live on Mars, you have to build first buildings, you have to grow plants so that you have oxygen which is produced and so on. This is a long way to go. Interesting problems, but I would not bet my money on this, that this will give a return in the next years.
Hello, Professor. I have a question about the way you power different robots, and mostly the robots today are powered by electric motors. But I've seen some robots being powered by hydraulics and pneumatics. Do you think in the future there are going to be different ways to power different robots, or are you going to use mostly electric power?
Of course, electric power has a huge advantage. It's easy to control, very precisely controllable, and it's high efficiency. Pneumatic and hydraulic. Pneumatic has some specific fields, but it's very much more difficult to precisely control it. Hydraulic, I see even more potential, and we have projects. We have actually big walking robots, which are walking excavators, Glauco knows this. He did some work in the back. Now we have really working excavators which can walk, but they are a couple 10 tons heavy. They can grab into the ground, but they still can adapt to the environment. So it's in principle force-controlled robots. But doing force control with hydraulics is very difficult, because you have this hysteresis in the whole valve, so we had to develop a very special valve for this. But on the other side, you can have much, much higher forces. So as soon as you really want to have, for example, in agriculture, in some field there will be hydraulics, because it's robust and you can generate huge forces. But if you want to be efficient, electric motors is good. Apart if you need to carry the power around with you. So flying platforms, even if these ideas of this flying autonomous flying taxis, most people think about batteries. I think it's stupid. Today, batteries are not good enough for flying because they're too heavy. For drones, it's okay, but if you want to build big airplanes for carrying people around, this will not work. Now we can hope that batteries come better. Batteries are not developing exponential, so we started with our solar airplanes. Since then, the batteries have probably increased about 30% in power density. In the same time, our computers were exponentially faster. As mentioned, the whole truck, the whole car was full of computers. Today, you have it on the laptop. But battery is still more or less the same size. So it's really depend on the applications and so on. But I think as long as you can use electric motor, do it, because it's the easiest to have very precise control.
Hi, Professor. Okay, hi, Professor. I've got a question. I don't know if you already answered it, but I really need to ask you. When you were talking about drones, technology of mapping, everything, I was thinking about that facility you showed a video, and I was thinking that sometimes there is people walking up there, and isn't there that more interesting to have technology on the facility to map it real time and give the location of the drone and everything to the drone, instead of having cameras and using technology to map every time? I don't know, I just want to know if it's more interesting to have the room doing that for the robot instead of having the technology on the robot.
Yes, it's an interesting question, and there are some people which really rely much more. I think we have more calculation power. Our lab is called Autonomous Systems Lab. My personal definition is about autonomous is everything on board. Now, why? Communication is never safe. So if you have a car which is relying on a signal, for example, the signal might come, the signal might not come, whatever reason. But you're not sure. If there is no signal, you don't know if there is something happening. Everything on board, you can actually have self-control. So in principle, if you have a sensor, you can actually have a self-check if the sensor is still okay. Everything which is cable, you can also have a self-check. But wireless communication through the air doesn't work. And I think most of you had this experience. Those who probably went in a robot competition and so on, this is always up to now in all events we were the disaster. That everybody is putting up his wireless network, and then there is something overloaded, and then your robot has no communication anymore. So I think it's important. It's, by the way, the same for cars. You can actually, through the network, you can get additional information. With autonomous cars, you probably will get an update of the map. But the system should still be able to survive without any communication. It's this is even more an open question with the flying platforms, because I'm convinced that we should actually have on board also everything. You can imagine this is a simple signal that each airplane, the bigger airplanes today have a beacon or a sender and receiver, so they know where the other airplanes are. And in the free space in the air, it's much more reliable because there is no obstacle around. But still also there. Today, people we want the pilot which is looking out and probably seeing an airplane which has no receiver and sender, or probably something is broken. And I think we have to have the same with drones, that we have onboard sensors which are at least as a second element.
As you said, some tasks are better performed by robots and some tasks are better performed by humans. But are there problems which are better performed by humans and robots working together?
Yes, of course. And I hope that this will be more and more, that humans and robots will work together. We have, I didn't show this slides where we have, for example, robots in construction, in buildings. Humans which are working in construction, very often they have at one point really pain in their back or whatever because they're carrying heavy loads. This should be done by robots. But a lot of very delicate tasks, humans are much better. And I think in a lot of fields there will be more and more that humans, robots really acting together. But we need progress. So this compliant actuators, which are soft and which are force controlled, this is required. Otherwise, humans cannot work close to robot. Industrial robots today, they have to be behind fences because they use all their power to go from A to B. And if B is here and your head is in between, you will be killed. With the new type of robot, which are flexible, even if you're all of a sudden run into a robot, the robot will feel it and stop, and you will not be damaged, not have any injury. So, but I think that's the way to go. Collaboration between robots and humans. Humans will be better in the high-level task, understanding of situations, and robots are better in some precision. It's the same as calculator. Today, people have a calculator, and we accepted that calculators are better to multiply 5,560 by 3,000, whatever. Computers are much better. We don't care. So it's not so bad. I'm happy that the calculator is doing this for me. Then I have more time for others.
Due to time constraints, we only have time for one more question.
Yes, loud.
We've seen some good examples of mechanical interactions between robots and humans, like the detector feedback haptics. But I would like to ask you what you think about the more cognitive aspect of interaction between robots and humans. Because, like in the example of autonomous driving, the task itself of autonomous driving is quite complex, but still, if you are going to make the technology practical and applicable in the real world, you have the problem of actually driving in a road where other people, other agents, other drivers don't actually follow the rules,
Yeah.
the prescribed rules, 100% of the time. And also, I would like to ask what you think that how is that for a robotics designer, an engineer, to acknowledge that and say, in order to make this work in the real world, I would have to break some rules, or it to know that other drivings are breaking rules, are doing unexpected things. Because I don't see how can you go to a policymaker, a lawmaker, and say, I'm going to make a rule that doesn't do the right thing all the time in order to behave in a way that other humans, in a way that you can interact with humans that don't actually follow that all the time.
So probably for those who didn't hear it's somewhat the question about should robots become more also like humans, so that they have a cognitive capacity which also allows to break rules, for example, in autonomous driving. And this is actually a very good example. So if you have a mix between autonomous cars and human-driven cars, there is an issue because the autonomous cars will actually not break the rules. It starts with the distance on the freeway, and then humans will actually always cut into the autonomous driving, and they will at one point not be moving forward anymore. And on the other side, autonomous cars today, which in a city where there is probably some weird situation. For example, there's a truck unloading some stuff. He's on the street, half on the sidewalk, and he's unloading something there. And there is a line where you should not go over the line. As a human, we will do it anyway if you can see that there is nothing happening, and even probably policemen will accept it.